Welcome back, ladies and gentlemen. Obviously, we've just finished up with forces on angles, and now we're going to be continuing with the last piece of dynamics, the last piece of two-dimensional, and that is inclined planes. Now, an inclined plane is just a fancy way to say a slope or a ramp. We're going to get a diagram up here. We're going to do some examples. Your notes cover this in some pretty solid detail. There's actually two different versions of the notes in there, if I remember properly, and an example. So we're going to do a little bit of a discussion, and then I will do the example, and then, of course, you guys are done dynamics. I will then, put together a digital quiz or something soon. Hopefully by the end of the week. Hopefully a little sooner, actually, but, we'll see how it goes. So, a reminder when it comes to dynamics. It's all about forces, and those forces can be in different directions. Now, inclined planes are a two-dimensional problem. What do I mean by that? This is a flat surface. This is what we've been dealing with up until now. Here is an eraser sitting on a flat surface. Surprising, shocking. This is an incline. You'll notice the eraser isn't moving. That tells us something, right? If something's not moving, that means the forces have to be balanced. Of course, the more I tilt it, eventually it starts to slide, just begins to move. We know that means the coefficient of static friction has been overcome, and it slides down the ramp. It pretty much never slides up the ramp unless you push it, but we could do that. So that's an inclined plane. How do we draw them? How do we use them? Well, an inclined plane is usually drawn as a little triangle because, again, physicists can't draw. So there we go. And we put a box on top of the triangle. So, now what? We've got four forces. We've always had four forces. Well, this one should be easy. Should. It points down to the center of the Earth. Well, if this was a totally flat surface, like, say, this one, then down would be this way. Right? So what's happening with this guy? Well, down is in the same direction. So down is like that. Okay, that one seems fine. Now, once again, we've got our example here. We've got this thing sitting here. Well, is this thing going through the floor? No, it's clearly not. So that means that there must be a force normal. Now, here the force normal points straight up. So the assumption is that immediately people go, oh, okay, so force normal must be like this. It must point straight up. Yeah, but it doesn't, because what is the definition of force normal? What does the n part of Fn mean? Does anyone remember? We could look it up. Of course, that's what we have notes for. Fn is force perpendicular to a surface. Okay. So here's a surface. I'm going to remove the eraser for a second. Perpendicular. That is perpendicular to the surface. It is sitting at right angles. Okay. Well, if I rotate the surface, take a look what happens to the force. It's on an angle. Well, that's a problem. I mean, I could keep going. That's still force perpendicular to the surface, but now it's pointing at a completely different direction. So Fn does not go straight up like that. No, it goes up at an angle to make it perpendicular to the surface. Lovely. So then what? Well, we have our object. It's sitting on here. Well, why is it not falling down right now? What's happening? Right? Something has to be stopping it from moving. And of course, what stops motion? Friction. We'll make it even simpler, right? I mean, simpler for our purposes. Right? If I was pushing up on this, it would move. But if I'm pushing up and it's not going anywhere, that means friction must be stopping me. Now, once again, on a flat surface, friction and force applied would be something like this. But on a sloped surface, remember, friction moves parallel to the surface. This is parallel to the surface. Well, the surface here is at an angle. I'm not going to have an arrow pointing into the surface, not like this. It's going to have to be parallel to the surface. And same thing with force applied. Let's just pretend I'm going to keep it all exactly the same as the one-dimensional example. So there we go. There's our situation. And I think you can definitely see that this looks bad, right? Because this one is the same, but then all the other ones are at an angle. And, I mean, we know what to do with vectors on an angle. You got to break them down into their x and y components, then you've got to add them together in order to find out what they exactly are on the axis. It's just a mess. And this is going to take us forever. Like, we have 3 different vectors that we have to break down and work out the answer to. Or will it? That's our usual frame of reference. Oh, there's a word from kinematics. Frame of reference, right? It's the orthogonal, normal frame of reference where up, straight up in the air is y, straight down is y, horizontal is x. And then z, of course, goes towards you guys or in towards the board behind me over there. If I take this and I hold it up like so, we can see that all of the different vector arrows are going off at angles, right? If I get out my trusty green here in order to show it more easily, right, we can say that FG is going down like this, and FN is going up like that, and FA is coming down like this, and F mu is going up like that, right? That's basically what we see there. There it is. And that is a pain. Those are all individual vectors that we're going to have to calculate with advanced vector notation stuff. We're going to have to figure all that out. Yeah, here's the wonderful thing. We don't have to do that. This is a situation where you can make things a lot simpler for yourself by changing your perspective. Because rather than this, let's get those other lines off of there. Rather than using the standard frame of reference, we're going to adjust. We're going to go from this to this. This to this. We're rotating our head with the inclined plane. And look what that does. FG is still pointing down, but now it's down at an angle. Well, F mu follows the x-axis. Fn goes straight up, and Fa follows the axis. By rotating our frame of reference, even just a little bit, the problem becomes much simpler. All we did was this. By rotating the page, we simplify the entire process. It's no longer about this. It's now about this. Huh. Crazy, right? The net result is that these 3 vectors we don't need to do complex vector addition for. We only need to solve 1. And anytime that we can make the work simpler and only have to do 1 rather than, 3, huge advantage. And what this means for our purposes is that all of these guys up here are exactly the same as these 3, but FG is going to be different because now FG has an FGY and an FGX. There we go. That is the only thing different about an inclined plane question. At this point, it's actually pretty straightforward, right? It's still adding. So everything that's going horizontally, you add. Everything vertical, you add. In this case, the vertical is FGY and FN. And the horizontals are F mu, FA, and FGX. That's all you got to do. We just add them. Now, our notes actually have most of this stuff written down, right? They say right in there, the sum of forces in the y should equal 0 because it's not floating up above the inclined plane, it's not falling down. But in order for that to be true, the sum of forces in the y is now going to be Fn and Fgy. Not Fg. It's no longer just Fg because some of the force of gravity is pushing the thing down the inclined plane. That's what we saw, right? If I take my little board again and I put the eraser on here, at first it's not moving because the force of gravity isn't strong enough, right? This force of gravity points entirely down. This force of gravity still points entirely down. The difference is now it'll make it fall. This force of gravity is split. Some of it goes down, some of it goes this way. The other big one that's going to mess things up, sum of forces in the x, let's say they're going to be equal to 0 in this case because the object's not moving down. Well, and that means the sum of forces x is going to equal in this case, force of friction, that's up, force applied, that's down, and force of gravity in the x, that's down. And that's the whole big thing. It's just gravity split in two. The last time when we were dealing with forces on angles, it was Fa that got split into x and y. Now we're splitting Fg into x and y. The process remains identical, it's just that we're splitting a different vector. Before we did the blue, now we do the green. The last thing to sort of throw out here is that we kind of need an angle in order to do this. Well, this angle here is the same as this angle here. So whatever the angle of the inclined plane is, that is also the angle of the force of gravity vector. And that's just because of the nature of how, angles work. If I increase this by a certain angle, then the difference between the straight up and down and the original direction is the same angle. So there we go. Those are the big surprises. Well, almost. There's actually one more surprise. Take a good look at this triangle. FGX. If I redraw this triangle, it would look like this. This is FG. This is FGY. And this is FGX. This one. What is it? What does that represent? You know. It's opposite. This one triangle breaks with the general pattern. Generally speaking, in most of our other questions, in order for us to get the x term, we would use cos, but not here. We can't do that. We are instead going to end up getting FG sine theta. And FGY is FG cos theta. And these are the points that most students have a hard time with. Like at this point, most people sort of go, okay, I get it. I just add everything that's in the same dimension, right? Everything that goes up and down, I add them. Everything that goes left and right, I add them. But the angle being different than normal, yeah, that throws people. They tend to make a little mistake like that. So just pay attention, be careful, right? And we'll do an example right now. That'll help, okay? So let's flip over here. If you're looking through the notes, the example's 2 pages in. Okay, so the example here in, let's see what we can do. So we're going to keep this diagram because it's going to be useful. Don't need this one. Okay. We'll just rewrite these so we can get lots of space. And let's fill in some information. Okay, so the example here says that the angle is 22 degrees. So this is 22 degrees. And that the mass is 50 kilograms. There's no force applied for this. And it says here that this is going to just begin to slide. Okay, so we're going to solve this in stages here. Right? Obviously, we need to find what the force of friction is to make this true. Right? We have an inclined plane, much like I've been using, right? This little board. We've got our eraser on it, and what I'm saying is that when I take this and turn it to 22 degrees, this thing here will just begin to slide down. Just start. So what's the friction for that? Well, we'll get there, but let's work it one step at a time, okay? First things first, Fg. What's Fg? Okay? Fg is going to equal m times g, just like normal. Well, the m here is 50, and this is 9.8. So we take this out, we go 50 times 9.8 on our trusty calculator, we get 490. And that's Fg. But we're looking for force of friction in the end. Right? We need to figure out what the force of friction is. So, if we're looking for the force of friction, well, how do we find it? Well, the force of friction is going to be one of the horizontal forces. And the force of friction there is going to be what? Well, there's F mu going up the incline, and there's Fgx going down the incline, right? This arrow down here, you can sort of move it up here if you really want. Like so. It's still in the same dimension, it was just displaced slightly. Okay, so we need to solve for this question, and we don't have this and we don't have this. Just begins to slide. Aha, we remember what that means, right? If something just begins to slide, that means that the acceleration is 0, which means that the sum of forces in that dimension must be 0. Therefore, 0 equals force of friction minus force of gravity in the horizontal. So that means that the force of friction has got to be the same as the force of gravity in the horizontal. Okay, that's not bad, right? This is the same as a normal question, right? We just made the two equal. We were just making sure to include the fact there's an x in there. That's the only difference. Okay, well, we have Fg. So Fg sine theta is the same as Fgx. So I could put here 490, and then the sine of 22. And that tells me that the final answer should be 183.6. Okay, it's not so bad. So what's the coefficient of friction? How do we solve that? Well, we take out our trusty formula for friction, the only other formula in here, and we look at that and we go, okay, well, this is 183.6. This I don't know, Fn. What's Fn? Why, it's Fgy. I can just plug that right in here. This is going to be Fg cos theta. Ta-da! Plug it in. 490 cos of 22, 183.6. So, we do a real quick calculation here. Take out our trusty calculator. We're going to get times 490. It's going to be 454. So then we got to have 183.6 divided by 454. That's going to give us 0.4. And that's correct. That is the final answer. So, yeah, it's not actually that hard. It's just make sure you understand what happens when you rotate it. That's the only key thing. When we went from this way to this way, it makes everything way simpler. And that is kind of the big trick. At this point, we can add in some forces applied, some other things like that, but we kind of don't need to. Right? It sort of solves itself. Anyway, you guys have loads of practice. Give it a try. Ask questions, of course, if you're stuck. I will work out solutions. I'll see about putting together a test on this stuff for later in the week. And you guys, of course, are welcome to do it as you are prepared. All right? So I hope you guys are having a good time and you are keeping warm. It's a little bit chilly outside right now, and actually it's a little bit cold in here right now. Let me tell you that. I think it's colder in here now than when it was winter. Okay. Talk to you guys next time.